Welcome, everybody. We're going to be looking at the chapter 1 contents here tonight. Part of the process of doing this will be to install the software we need to code with. So we will get to the point where we're doing a little bit of sample coding to make sure everything's working after the install. But I also want to kind of show you kind of the general lay of how the book reads and some of the features of the book. And I find, doing a lecture like this, for me, works better going straight off the book than it does from the PowerPoints. So this is kind of like a read through of the chapter without reading every darn word to kind of reinforce your learning and what's kind of important. George, did you have a question? You're good?
Sorry. No, I was waving at my wife who was going to bed.
Okay. Hi, honey. All right. Well, welcome to live class sessions, folks. All right. So here we are covering chapter 1. At the beginning of all of these chapters, kind of like I do in my unit folders, right? I tell you what you're going to learn. These are the key things you're going to walk away with. So we're going to learn about computers and programming. I'm not going to do a really heavy lift on computer history. I do have some other videos that are posted in my archives, which I would encourage you to watch where I do. And I think some of that stuff is really, truly fascinating. But in the interest of time, I'm not going to spend a lot of time there. We are going to actually get into the Spider IDE tonight and write a little code, at least hello world, to make sure it works. And then we're going to talk about the difference between runtime errors, compile time errors, and then we'll once again very quickly hit the topic of algorithms and pseudocode and why they're important as we round out the chapter. Whenever you read one of these chapters, they'll have this listing at the bottom where, like, if there's stuff that's designated towards like data science or whatever topic it happens to be, they indicate like, what that's attached to. And they have like basically these little addendums that they throw in. Some of them will hit, some of them will not. All right, so going on to the very first section here, basically, I like to think of computers, and when it was first described to me, right, learning how to code, I had this teacher, and she's probably gone by now, I'm sure. Very brilliant lady, very nice lady, who said, computers are just dumb machines, right? They're no smarter than an automobile. Well, you think automobiles are pretty smart these days, but basically it's a collection of like machine things, like electronics and parts and, physical things that really don't know what to do unless you tell them, right? The way that we tell a computer what to do is by writing a computer program. The computer program is a set of instructions. Even the operating system that runs the computer, like Microsoft Windows or the Mac OS, that's software that tells the hardware how to interface with the user and the screen and the storage and the CPU and the memory. That's what an operating system does. Then we create software programs or applications that run over the top of the operating system that allow us to perform specific functions, whether it's creating art or writing a document or playing a game or whatever, creating a flowchart, right? There's differences obviously between software and hardware. Like the physical computer is called hardware. The stuff that is the instruction sets, that's the software. You don't technically see that unless it's on a disk, but you're really not seeing the instructions. You're seeing the delivery mechanism for them. And software really, frankly, can be used to do a lot of different things. Pretty much anything you can imagine, all the stuff I mentioned, and then some. And then maybe your position in life is to come up with that new killer app that nobody has thought of before and make billions of dollars and, fly up to the moon or whatever, take a spacewalk like a billion. Or maybe you'll just like build a website, or maybe you'll just build a simple app that helps people, whatever it is. That process of creating the software is called programming, right? Programming has a system or a methodology to it. I've talked already about like the input processing output thing. We've talked about the ways to solve logical problems with sequence selection and repetition, and all of those techniques apply to programming often before you write the code. But ultimately, your goal is to write code. So moving on. All right. Now, computers work with a bunch of physical hardware. They attempt here to talk about the key parts of a computer. Um, the thing that drives most of our technology today, whether it's a smartphone or a laptop or a tablet or a desktop or whatever, somewhere on that system, there's a central processing unit, which is this tiny little chip with tons of little micro pins on it that sits in the socket. That chip literally has billions and billions of transistors embedded on it. It's huge number. I don't even know what the number is, but it's like billions and billions. And then when we have computer systems that are multi-core, like most of our systems are, like my system here, I'm not even sure how many cores I have, honestly, but I guess we can pull it up. And so I'm running 6 cores. Each one of those cores is split into 2 logical processors. So in essence, I'm kind of running, 6 CPUs or 12 CPUs, depending on how you look at it, right? So why do computers have multiple CPUs? Because about 25, 30 years ago, they ran into this like limitation on the capabilities of a CPU and factors of like heat, data transfer, etc. That basically they hit like a wall. So instead of like, we can't make these CPUs any smaller and more efficient. So what we have to do is just have more of them, and they all work together, right? And that's really common. And then CPUs kind of extend out to GPUs, right? Our graphics cards now sometimes have better processors than our main system board does. Really interesting, like some of the new like Mac chips, like the M series chips that they have, many of them are like, for example, my simple little M1 MacBook's got 8 CPU cores, 8 GPU cores, and 12 machine learning cores. Like, holy cow, how many processors is that? I lost count already. It's like 30 processors or something, 28 processors. I mean, wow, right? That's a lot of processing capability. We have storage on our computers, so we think of primary storage and secondary storage, and this is really kind of a weird thought, but primary storage on a computer is not your hard drive. It is your RAM. It is the memory of your computer is primary storage. That's what the computer thinks. Unfortunately, primary storage, when you turn off the power, whatever's in there goes away, doesn't get saved. So then we have secondary storage to store that information permanently. So when your computer starts up, it really doesn't know what to do. There's a chip built into the system board called the CMOS or the BIOS, right? That has an instruction set that says, hey, go get that hard drive. Here's the kind of hard drive you have, right? That's where you're going to find your operating system. So it goes to that hard drive, it finds the files and loads up the operating system. Once it loads up the operating system, then the other software can get loaded up too, but it reads it off of secondary storage, loads it into primary storage, and then your computer's up and running, right? Old-fashioned hard disks, right? Not like the one I was holding up before. This is a spinning platter hard drive. It's kind of like a record player, except the disks are magnetic, and it's got little arms, and sometimes there's stacks of disks, and the arms go really super, super, super close to the disk. They never touch, by the way. They're like less than the width of a human hair off the surface. And then if there's multiple disks, they have arms that go to both sides and in between, right? And it works like a record player does. It spins really fast, right? They're rated by their speed, actually. And then the arm moves around. So when it gets an instruction to receive a piece of data, that arm's got to physically move to that spot. And then it magnetically gets charged and reads the information on that disk. You know where like hard drive crash comes from is when that arm touches the disk. It's not supposed to. That's a crash. Right? We think of crash as like when your software is not working, but the reality is a hardware crash of the hard drive is really the computer crashing. Right? These days, we all use SSDs, like the one I was holding up before, which is like a giant flash drive. It's just a bunch of transistors and stuff. These process and move data significantly faster. One example I always give people is I have this old laptop still sitting here. It's Windows 10, or actually probably started on 8. Had a spinning platter hard drive. I would like boot that thing up. I would wait like 5 minutes for everything to load, and then I could use it, because it just took that long, right? Then I took that same configuration, loaded it on a solid state drive, and the thing was booting in like under 20 seconds, ready to roll. And then everything else was faster. So why have an SSD? Because it's so much faster. So don't ever buy a computer without an SSD anymore. One problem with the SSDs, though, that's kind of interesting, is if a spinning platter hard drive fails, you can almost always retrieve the data from it. There's tools that can extract the data. Like if your arms break or whatever, there's tools that can retrieve that data. If an SSD fails, it's done. So if you're putting stuff only on an SSD, you better make sure you have a backup. You should always have a backup of all your data, by the way. Computers these days often are connected to the outside world on a network, right? In fact, there was a time in computing where it was like unusual to have a network at home, and it was unusual to be on the internet. Now, if we don't have that, like what good is this? We can't connect to anything, right? So we connect to the internet through networks, both local networks at home, and then the internet really is just a network of networks. And then they have little diagrams here of like hardware and whatever. I'm moving on. All right. A lot of really interesting computer history, but we went very quickly, by the way, from introducing electronics to computing devices. So computing devices have existed, at least modern man thinks, since maybe the early 1800s, mechanical calculators and tabulating machines that were programmable. And the reality is when you really start to study history now, they've been discovering devices, the Antikythera mechanism, and I should probably pull that one up because that one is highly notable, because they basically found this in the bottom of the Mediterranean Sea in a shipwreck. They pulled it up. They didn't know what it was. They ended up x-raying it and figured out that it was this machine that was really, really complicated, very complicated gears and levers and motion, that dates back at least 2,500 years. This is like mind-blowing stuff, because basically what it was an astronomical calculating computer. It could calculate like eclipses and like what astrology sign is current and calendars and stuff like that. It was a mechanical calculator, and we thought that we invented that. Let's see if I can spell this stuff. We came to the 1800s and we had this guy named Charles Babbage. Here's a picture of him, by the way. And he came up, he didn't actually build it. He came up with the design for the analytic engine, which was going to be the first programmable mechanical computer. He never lived to see it built. Somebody else took his design and ended up building it, and it worked, right? So you could input a formula like we just kind of did with our algorithm, throw in a couple of numbers, turn the levers and the cranks and the gears and all that, and then it would like display the answer with like knobs and levers, and it didn't have a keyboard, folks, right, or a screen, right? It was mechanical. Interestingly, his girlfriend, I don't know if it was his girlfriend, but his acquaintance, Ada Lovelace, was the one who wrote the first working program for the device. And then when the device was actually built, they tested the program. This is a for real thing. She sketched it out. She figured out the concepts of like variables and loops and algorithms and sequential steps and all the stuff that we do now. So sorry, guys, the first programmer was a girl, not a guy, right? And very interestingly, the document that you see in the background here, which was the first program that was written, recently went up for auction like 5 years ago or something like that. And it sold for $250,000 for that piece of paper, because it was the first computer program. Interestingly, this guy, Herman Hollerith, and this will appeal to the SD students in the class here. He took that analytic engine, which was able to tabulate stuff much more quickly and accurately than humans could. And he built it into this machine here, which he combined with punch card technology to basically rapidly calculate the US Census in the late 1800s. I think by 1890, he had this machine up and running. And so basically the census takers would gather the info, punch the info into the cards, put it into the machine, they would run it, and then the gears and the levers here, whatever, these little dials would record the totals. And so they could do the census data instead of taking them like 10, 15 years to tabulate a census, because they had to collect the data and then tabulate it. They could just put the punch cards in the machine and run it, and it'd be done like in a matter of hours or days, right? He took this invention on to create a big IT company that still exists today called IBM, right? So this is the precursor, folks, to all the programming. Very interestingly, the punch cards that he used, right, look like this. These were actively in use in computer systems well into the 1980s as an input mechanism, as a programming tool, and an output mechanism. And for the older folks here in the room, like myself, do you guys remember we used to get our like Wisconsin gas bill, and it used to be like on a punch card because it got output from one of those systems, like this antiquated mainframe system, and you would get like a punch card in the mail and say like, you'll eat this so much money you owe. But these were both input and output mechanisms and storage. Kind of interesting technology. Ultimately, we got into this age where we had adding machines, and I'm totally misspelling here, right? That were mechanical adding machines that were just basically variations on that analytic engine and the IBM technology. Gears and levers and mechanical parts on the inside doing the tabulations. These types of adding machines were actively used in accounting offices well into the 60s and 70s, and then became calculators, which cost a fortune for electronic ones. But these are basically tabulating devices that were mechanical or electromechanical. So they had electricity powering it instead of the lever. But man, I remember going into the Kohl's food store up in our neighborhood when I lived, in Milwaukee on like 35th and Juneau or something like that. And the cash registers were these like click, click, chick, chick, chick. And I don't know if you guys, George Martin, I don't know if you guys remember those machines, but those were actively in use. And those were, electromechanical devices once again. Now, a lot of stuff was happening up into the mid 20th century. The Germans, the British, the Americans all had some form of electromechanical computing devices. The Germans got pretty advanced with theirs pretty quickly, and they created one of these called an Enigma machine, which is basically one of the world's first encryption ciphering devices. So they would use this during World War II. The Germans did. They would take a message that they would want to send out over radio waves. They put it into this machine and they would type their message in, and then the machine had a cipher built in, then it would output it a different way, and the ship captains knew how to read that code, and the code would change every day. They would use a different cipher every 24 hours. And because they were able to send coded messages to their ships, they were kicking everybody's butt in World War II because we couldn't figure out what they were doing. The British were working on a countering device. They hired this guy named Alan Turing, who built this machine, which is another electromechanical computer that would take those codes and try to break them. They did eventually break the code, by the way, so they could read all the German messages and then thwart all their strategic efforts, right? What I find really fascinating about this is that, had this not happened, we may all be speaking German today just because of this one device. What I find really fascinating is that Enigma machine, the Americans ended up capturing a sub in the Atlantic captured one of these devices, and you can go down to the Chicago to the Museum of Science and Industry and see that submarine and one of these machines. I don't know if they let you touch it, but you can get really close to it. Right? Pretty fascinating stuff. After the war, you know, the Russians and the Americans raced in to basically steal all the brain power of the Germans, because they were really advanced on this stuff, by the way. And they ended up building, the Americans did, the world's first fully electronic programmable computer system without mechanical parts running it. So no gears and levers. It was all like relays, vacuum tubes, switches, patch cables, and lights, basically. So big, and so much, so heat generating, that they needed 5 central air conditioners to cool it down enough to have it run, right? But what it did bring to us, the fact that we could put in more complicated mathematical equations, like trig calculations. For example, the Germans in World War II not only built rockets and jet planes before anybody else had them, thanks to these technologies, but they were able to take those rockets and launch them from, Central Europe, or, the German mainland, shoot them over the English Channel and land with high precision in England, destroying things. You know the kind of math it requires to figure out the weight, the force, the propulsion, the angle, counter for wind speed, and have it land in the right spot. I mean, that's advanced, complicated math that people up until that point were doing with slide rules or calculating by hand, right? These machines allowed you to put in a formula, crank out the responses really, really fast, and really changed the face of the war. The fact that we built this was used to help do calculations to build our first rockets and bombs and jet planes, and really kind of gave us an edge over a lot of different countries. The first fully programmable electronic computer. The primary technology that drove this was vacuum. I can't even spell it. Vacuum tubes. There we go. Right, which look like this. Guitar players know what I'm talking about. These are basically like light bulbs that generate a lot of heat. Each one of these vacuum tubes is basically, the equivalent of one singular transistor. Kind of an interesting kind of side story, and I don't want to forget this. I think it's in the book, right? They talk about the first computer bug. So one day, and I think this is at over at Harvard, they had a Mark I computer that was kind of, cloned after ENIAC. The program wasn't running and they couldn't figure out why. And somebody traced it down. They figured out, hey, this relay is shorting out. They opened up the relay, and inside the relay was a moth shorting out the connection of the computer. So they removed the bug from the computer. So they debugged the computer. So that was the first computer bug right there. It was physical. They taped it into their log book, right? So kind of really funny stuff. All right. So from vacuum tubes, we moved on to transistors, which were much, much smaller. These are tiny. And then from transistors to integrated circuit, where they took a whole bunch of transistors and put them on one chip, which then led to modern CPUs, right? So we go from like a bunch of single vacuum tubes to single transistors to integrated circuits to CPUs. And now we have literally billions and billions of transistors built into these things. And they're like this big, folks. They're barely the size of a penny. Like you might buy a CPU and it might sit on a thing this big, but the actual CPU is like minuscule, right? So we went from ENIAC to like, I don't know, Terminator or whatever in like decades, really, really quickly, really, really quickly. And now, the whole thing is we have more computing power in the palm of our hands than they had available on the entire planet Earth when they put man on the moon. Right? And what do we do with it? Facebook, Netflix, Angry Birds, whatever, whatever game you're playing. All right, so I'm going to go back to the book now. All right, so that's ENIAC. And we have come a long, long way, folks. All right, so here's what we're going to do next. So we're going to look really quickly at Guido, who was the guy who invented Python. He did so back in the early 90s to automate server tasks like we talked about before. It's gone on to become arguably one of the most important programming languages. What we are going to do next is we are going to install Anaconda, and I think I have a link in the course shell here. What I would like somebody to do, though, is somebody out there that does not have it installed, that's fairly computer savvy and screen share worthy. And Alex has his hand up. So what? All right. I saw Alex first, Juan. Sorry.
Oh, no, you're good.
So Alex, if you could share a screen, I'm going to flip a switch here, and we're going to coach Alex through the process. You don't have to wait for me to stop sharing. You just go directly to it and share your whole screen if you could. All right. Now, what I'm going to do for you is I'm also going to share with you, the link is in unit X. And if, you know what, I'm just going to give you the direct link. So I'll just drop it in the chat for you, unless you're already there. Oh, he's already there. All right, fantastic. All right, so go to the download page, see where it says free download.
Where?
Way at the top, right next to the sign up button.
All right.
There you go. All right. This should work on Windows, Mac, or Linux, by the way. All right. And you just got to follow through their process here. See, notice the registration screen below submit says skip registration. Yeah, so you don't have to register. If you want to be polite, you can. I assume you're on a Windows system.
Yep.
And are you sharing your whole screen or just your browser?
Should be the whole screen.
Okay. Because I'm not seeing like your Windows toolbar unless you're auto hiding or something.
Yeah.
Oh, yeah. Okay.
This?
Yep. All right. Go ahead and hit the download. I do want you guys to notice that the current active version of Python is 3.12. So that's the version we'll be installing today. I think I have that version on my machine. I may or may not. We'll just watch the download happen here.
Quick side question. Do you want to
Yes.
go over this too?
No.
Downloading the library?
Yeah, you don't need to. The beautiful thing, so Alex, you're coming at this from a software developer standpoint, right? Like, that basically the libraries for a language are really what allow you to create the code and run the code. And then you download a tool to create the code, right? The Anaconda distribution does all of it. So it installs Python and all of its libraries, a few different IDEs and prompts and stuff.
I don't need this.
Yeah, you don't need to do the library install. That is an approach, though. It is a possible approach. We like the Anaconda distribution for a number of different reasons. It is built for doing data science and artificial intelligence work, and also for general purpose computing. So if you're writing just regular apps and programs or websites or whatever you're doing, it'll work for all of that. Because Python is so heavily used for data analysis, scientific purposes, all those types of things, and artificial intelligence, a lot of those capabilities are just part of what we call this distro, right? So Anaconda is a prepackaged distribution. It's recommended by our author, very simply because it is by far the most popular one in terms of providing all those tools without needing to go find additional libraries and not have like multiple install steps or multiple things to download and configure. It's like one smooth process. The tool that we'll be installing shortly will be Spider that's part of this package, and then we will fire that up and run it. Can I just see a really quick show of hands though for the people here in the session? How many of you already have this stuff installed? Just did it on your own? I know there's a few, right? All right. All right. So good number of you. So Alex, right now we're in the process of waiting for your download to finish, right? When you do finish, I'll give the screen back to you, but I'm going to take the screen right now because I want to do a really quick demo of how to test Spider.
Oh,
What
I was gonna
one-
say I have it ready to go to the next if you wanna go to my screen for the people that don't have it. Up
You
to
know what, Juan, let's do that. You know what? Go ahead and go directly to share. Right. So this is like the speed it takes is a combo of like your hardware, right? And your bandwidth, right? So like if you have a really fast internet connection, it'll download faster, right? So Juan's ready to go on to the next step. So go ahead and click next. Then you have to agree, like you have a choice. And then it says just me or all users. You're probably not multi-user, so just me is probably fine. And then I go with the default spots unless you have a spot that you prefer.
Sure.
Yeah, I would just take all the defaults. And you can see the install actually goes pretty darn quick because most of the stuff we're actually downloading, the install process is not really installation per se, where it embeds into the operating system so much. It really is more of a decompression of files and folders. Python at its core is a library of pre-built programs that allows you to code, debug, and execute that code. One thing that's really fascinating about Python as a language, and if any of you who have gone through traditional programming courses, Python is not a compiled language. That means when we create files and programs in Python, it does not create an executable. If I were to create a program in C# or Java, I'm creating an executable file, and then I can take that executable file and deliver it to somebody, say, here's the app, go ahead and run it. Python is what we call an interpreted language, which means that it takes your instructions and executes them. It does not compile. It never turns into an exe. Not that it's not possible to make that happen, but generally speaking, there's no need to make that happen. The other language of great popularity that is directly comparable would be JavaScript, which is also what we call an interpreted language, meaning that it just executes instructions. The difference is JavaScript typically operates in the browser. Python operates in the operating system. All right. So I'm just giving you this info as we're watching the install go. And Alex, I'm not sure how yours is going. Sometimes what I do, Juan, is I click the show details so you can see the stuff it's doing, right? Because it's doing stuff, right? You're just not seeing it. And most of what we're waiting for now is mostly decompression of zip files is really what it is. And there you go. Go on to the next step. Yep. And then I'm going to let you launch the Anaconda Navigator. So what's going to happen now is the Anaconda Navigator is the launch point for all the products that come with the Anaconda distribution. And Juan, if you don't mind to continue to share your screen.
Yeah, no, that's fine.
But let me ask you to do one thing. Could you make that window full screen?
Yeah.
And it's kind of ridiculous on
Or
your
the
end,
other
but-
one, or this one, right? You want this one?
Yeah, I want the Navigator. And it's already asking you to upgrade. Say no, remind me later. Right. All right. So once you get into the Navigator, this is basically the launch point for running all the stuff that comes with or stuff that you can add. So you'll notice that some things will say install. That means they haven't been included, but you could try them if you wish. But the two main products in this that we're going to use for this class will be Spider, which you see in the second row, and the Jupyter Notebook in the top row. Those are our primary tools. Go ahead and launch the Spider IDE. And you guys can try this at home if you want, or you can just watch Juan and try it later yourself. So Spider is what we call an IDE, and I should explain, just dismiss for now. Let me explain what that acronym means. IDE stands for Integrated Development Environment, meaning it will provide a number of resources for us. First, a window to type our code into, another portion of the screen where we will see the code execute, and other portions of the screen where we can look at various tools like the value of variables, or look up the meaning of certain things, or interact with our files, right? So it's all in one package, meaning I can write the code and test it all in the same product. What I'm going to do right now, Juan, is I'm going to draw on your screen, if you don't mind. So this part of the window, this panel, this is where we code. This down here, we call this the console. It's the output window. That's where we see the results of what we do. And then this is kind of a utility window, and you can see there's like a help menu, variable explorer files, and I can't read the other one. I rarely use that panel, so often I arrange my windows, so it's like really heavy on the code. Now, when you first code, and we're gonna coach Juan into doing his first program, but I'm gonna make you make your font bigger first. So click into this panel once, just click, and then hold down your control key, and then press the plus key on your keyboard. You should be zooming in. Yeah, keep going, bigger, bigger, bigger. All right, that's pretty good right there. All right. I'm going to get rid of the X, don't worry. All right, so right there on line 8, I want you to type the following command. Type print, all lowercase, caps lock is on. Open parentheses.
Open parentheses.
Yeah, so the shift of the number 9 key. All right, see how it closed it for you right away? Now type a double quote, which is the shift of the, what is that the shift of?
Like this one right here?
Yep. And now inside those double quotes, type hello, Racine or Kenosha or wherever you are. All right. All right. Now you're going to run your first program. You ready?
Yep.
All right. Up in the toolbar up above, you see a little green play button.
This one. Yep.
Yep. Hit that
Run.
button. And yeah, run with the default configuration. That's fine. And then notice in that panel, you can click in that panel and do Control Plus also. It will make that one bigger too.
Nothing.
Nothing.
No.
All right, try holding down Control and scroll forward on your mouse.
Nothing.
All right, well, don't worry about it, but I don't know if you guys can see it, but he's got the output of his program. It says which file he ran, where it's located in his file system, and then the output. So this is the most primitive of programs, right? But we were able to give Python an instruction to output something to the screen, and it worked. And as simple as it is, welcome to Python programming, Juan. Right? Hopefully all of you guys are trying this. All right, so we have to end class now, so this video will end here.